This is stop one on the geology field trip. We're sitting in Slate Quarry here at the western tip of Montgomery County. Just a little bit up the road is the county line to Frederick County. Geologically, we're in what's called the Westminster terrain of the Piedmont Geologic Province. This rock here is called the Ijamsville Phyllite, or the Ijamsville Formation. Something that I never mentioned in class, if you're looking at rocks in an individual area, just about all of them have a geographic name. So rather than the geologist or whoever is talking about having to say, that slate that we had over there in that quarry, but they give it a local name. So this is the Ijamsville Phyllite, or the Ijamsville Slate, or the Ijamsville Formation. Often the rock name will vary a little bit. Some people call this a slate, some people call it a phyllite. It's just about on the border. I don't know if this shows up in the picture there, since it has to reflect just right, but this has a silky shine to it, and so I would call it a phyllite. Can you see the shine off the surface as I turn it? That is the foliation, or the cleavage. I've never been able to see any bedding in this at all. In the lab, you have seen samples of slate that do show at least a little bit of bedding. This doesn't seem to show any. There may be some other places where the Ijamsville does show bedding, but I haven't seen them. The fact that there isn't any trace of bedding here indicates that this particular sedimentary, when it was still a sedimentary rock, was deposited in an exceptionally uniform environment that didn't vary at all from day to day or from year to year. It was very, very, very steady. And pretty much for that reason, it's believed to be a deep water deposit, because deep water is a very uniform environment that doesn't tend to change much. There are exceptions to that. If you get turbidity currents on the slope of the continent, then you do get graded bedding as the turbidity current goes down the slope, slows down and deposits coarse and then fine, and the next current will do the same thing, coarse and fine, and so you get an alternation there. Here, there was no alternation at all, and so this is definitely not a turbidity current deposit. It's just an area of very deep water. What's interesting is that when we go up a couple of miles up the road, our next outcrop, which is very close, definitely shows very strong bedding in it, and it varies from siltstone to a fine-grained dirty marble. And you can see the various layers. You will see the various layers very obviously. It's calcareous also. It's got calcite in it. I brought along some acid. I'll be able to demonstrate that. And the question then arises, what's the relation between this rock here, which is so very uniform, and that rock up there, and from there westward all the way to Utah? The rock is not deep water. It's a shallow water rock in which my first Parula warbler of the year. The answer to that, well, the question was raised, I guess on the order of 100 years ago now, when the local geologists working in Pennsylvania found that they could draw a line on the map, and on one side of the line, to the southeast of that line, it was all rocks like this, very deep water rocks without much bedding in at all. And on the other side, all at once, after you crossed this line, it changed to rock with strongly obvious bedding in it. They had no idea what the line meant, what caused that line, so they just called it a line. And they named it after the town of Martik, and so that's where we get the Martik line from. Today, we know it's a major thrust fault in which the deep water rocks off the coast of old North America were pushed up and over the shallow water rocks when the first collisions took place offshore. And of course, at that time, talking about collisions of major chunks of rock would have been heresy. That was considered science fiction. However, the fact that it was a thrust fault, whatever the cause for it, that became evident after people did more mapping. The shallow water, deep water line can be followed all the way from Virginia and Maryland and Pennsylvania northward. And you get up into New Jersey and New York and Connecticut. It's given a different name. It's called Cameron's Line there. For the same reason, the geologists there noticed the same sort of difference and had no more explanation for it there either. And it was a geologist named Cameron who first pointed this out, and so it's Cameron's Line. It too is a major thrust fault. Whether it's continuous with this one or not, I don't know. If it has not been demonstrated to be the same, that would be a very nice master's thesis for someone, to try to work out the relationship between Cameron's Line and the Martik Line. It very likely, it's such an obvious question that I'm sure someone has worked on it. I just don't know about it. Okay, so much for this right here. I want to go over there and look at the other side of the quarry now. There's an interesting point over there. You want to get set up over here. Do you know what this is right here? Just looking at it, can you take a guess? I'll give you a hint. If I put acid on it, it would not fizz.
Calcite?
It's white.
Does not fizz.
Okay.
I did that eliminated calcite. At one point, I think I told you, if you're ever out walking in the woods and you see a white rock and you don't know what it is, and if you go by the odds, what should it be? What are the odds? Quartz.
Oh.
Thank you. Yeah. This is a quartz vein here. You can see running across the foliation of the slate, and that actually doesn't fit into the three categories I gave you a rock. It's certainly not a sedimentary rock, not with a layer like that cutting right across everything else. It's not an igneous rock because you can't. It turns out quartz melts at something like 1800 degrees Celsius, which is fantastically hot. And there's no sign of heat like that next to that quartz vein, nor next to any other quartz vein either. And quartz veins are very common things. So it's not melted quartz that's hardened. It's not an igneous rock. It's not a metamorphic rock. It's a hydrothermal rock. In this particular place, this was a crack in the rock along which superheated water was flowing. Superheated, like maybe 300 degrees Celsius. Well, we knew that already, that it was at least that hot here, because this is a metamorphic rock we're looking at around us. It's low-grade metamorphic rock, so it wasn't super hot, but it was hot enough to give us the pressure enough to give us the cleavage. So if this didn't come from melted quartz, what did it come from? Well, I used the word hydrothermal. Do you know what hydro means?
Water.
You got it. How about thermal? Well, that's an easy one.
Thermal is like hot, right?
Hot.
Yeah.
Hot water. It turns out that extremely hot water will dissolve almost anything, including quartz. Now, this rock around us was cooked. Again, I repeat myself. It's a metamorphic rock, and metamorphic rocks are cooked, and they're cooked to somewhere in that vicinity, enough to make new minerals and to develop the cleavage. And one of the things I mentioned when I talked about metamorphic rocks is that one of the main processes in metamorphism is dehydration and decarbonation. In this particular case, dehydration. The deeper rocks, when they're heated up, lose their water. The clay minerals are quite water-rich. The water is driven off and it rises into the overlying rocks. You're going to get hot springs, among other things, although that's when you get a lot closer to the surface than this. But when they rise into the rocks above, the water begins to cool down. And as it begins to cool down, it can't hold nearly as much material in solution, including the quartz veins, including the quartz. And so it deposits veins of quartz in the cracks in the rock. Now here, it's not of extreme interest, but if we were down by the C&O Canal, which is quite close to here, by the way, there are lots of quartz veins in the rocks there. And they are quite interesting in that they contain gold. They do today. There is still gold there today. As a matter of fact, a friend of mine, dead now, but he gave his fiancée, later wife, a ring made of gold he personally had collected. You know, it's certainly a lot cheaper doing it that way than going out and buying a ring. But if he'd gone out and worked at McDonald's at minimum wage, he could have gotten the money and bought the ring a lot more easily. So it's not that he was trying to save money. The thing is, although you can still collect gold today, it's not a way to get rich. Here's a question. If there is still gold in those rocks, why aren't there gold mines still working there today? Well, the amount of gold in the rock is very, very small. You could get out though, and if you get several tons of rock, maybe you'll get a little bit of gold out of it. That's several tons of rock. If you do that, then you have this enormous pile of waste rock that you've got to get rid of. Well, if the mine were in Montana, or even better, Nevada, where you've got miles and miles of nothing but miles and miles, you can just dump the rock and nobody's going to worry about it. Try doing that in Montgomery County. If you were going to do it here, you would have to find a way to dispose of that rock without just dumping it in somebody's backyard, so to speak. And you could do that. You could ship it out into the Atlantic Ocean and dump it in the deep ocean. That would work. There would be some squawking about that too, but you could get away with it. But now, you take that rock and you get, let's say your ounce of gold out of it, which is now, I think, worth about $1,600. And it's going to cost you $1,000 just to get it out of the ground and get the gold out of the rock, and another $1,000 to ship the rock out, ship the waste rock out. It's going to cost you $2,000 to get that ounce of gold, which is worth $1,600. That's why those mines are not working today. I tell people that yes, there are indeed gold mines in Montgomery County. They're called real estate offices. So if you can figure out a way to solve that problem to get the gold out more cheaply, then you could mine that gold today. It turns out, by the way, that the cheapest ways to get gold out of the rock are to grind up the rock and then treat it with one of two things. Mercury, which will combine with the gold, and then you treat the mixture of gold and mercury and get the gold back out again. Because mercury will grab onto gold very nicely. What do you do with the mercury, which is very, very toxic? Then disposing of the mercury is going to be a bigger problem than disposing of the rock. The other thing you can use to grab the gold is cyanide. Cyanide grabs onto gold too, so you run a cyanide solution through the rock. It grabs all the gold, you can extract the gold from the cyanide solution, and then you get all that cyanide to dispose of. And as everybody knows, cyanide isn't very nice stuff either. Now, as to why is there gold in this rock to start with? Gold is not very soluble at all, even in very, very, very hot water, unless you've got some chloride in the water. Chloride like sodium chloride in salt water. Chloride is another material that has a very strong affinity for gold, and if it's both very, very hot and contains chloride, it will extract gold from the rocks that it goes through. And then when the water cools down and starts depositing quartz, that's just about the same place that it starts. The chloride starts letting go the gold, and that deposits the quartz with the gold. If you go to California for the gold rush back in 1849, they mined, originally they took the gold from the streams in what are called placers. You wash it with a little pan and you can collect the little gold grains in the bottom of the pan because they're very heavy. They traced that back to the foothills of the Sierra Nevada and found that the gold in the ground was in the quartz veins, and so they then put in bedrock mines to extract the gold there. And they didn't worry much about waste. They just dumped it wherever it went. They didn't. There's lots and lots of land, not many people, and the hell with cyanide or mercury or whatever else you left around. Whether that was a good idea or not, well, it was a good idea for the people who were mining the gold. Yeah, what am I?
No, the sun is in.
Okay. I thought you were signaling to me. Anyway, so this my guess is that somebody has checked these particular gold veins, particular quartz veins here for gold, didn't find any because there have never been any gold mines right in this area. But that's why there is gold still located in Montgomery County. Okay, any questions? Okay, we'll go to our next stop, which I'll mention is just, as I say, a couple of miles up the road on the other side of the Martic line. So we're crossing a major boundary here between two completely different terrains.